हेलो हाँ सही है अमरान भाई दे उधर रोटी दे वहाँ कहाँ मंगाना था रोटी बोल उसको भाई वो बोल लो मांग लो
हाँ ले जा
जो लेना आप ले लो
नहीं हाँ अभी आलू खा रहा है
अरे दोनों तो भाड़े हैं रे बाहर से रखना बाहर से भाई इतना देरी लगे अभी तो घंटा पहले ना
आप यहाँ पर खड़ा था
मतलब उसमें लिखा है एडवर्टाइजमेंट यहाँ पे
वीडियो तो नहीं है ना
जूम करके लो ये एक बार थोड़ी सी जूम करके लो एक बार
क्या टॉपिक है आपका आर्टिफिशियल न्यूरल नेटवर्क है तो
हाय हाय
वो कहाँ
हाय
मेरे से पापा को बोलना पापा को
गई बढ़िया रास्ता हो गया तब क्या
सब जगह होता है
नहीं कॉम्पोजिट में यही तो बोलो
ये मैंने क्या है डाटा के अगर
मेरी याद है ही नहीं वैसे 3 वीक्स का तो रेस्ट बोला ही हुआ
गवर्नमेंट जैसा समस्या है ना ये सबसे ज़्यादा टफ रेट होना चाहिए और इसकी टेस्टिंग 100% एक तरह से हुआ या बोले तो जगह हुई इसकी टेस्टिंग 100% हो गई अब ये
मेरा पापड़ भूल गई जैसे चावल ले आई
अरे यार वो
कर देते हैं माँ बाप है ना नहीं निकाल पाए तो निकलने काम
घर में नहीं रहा हूँ
ले और दे देता हूँ एक बार
Only vegetable. Only we don't buy very expensive because it's in operation.
नहीं सर
The onion is maybe the hidden bomb.
Because more shiny better, or it will be more spicy. Well, a lot of
They are doing
राइस दे दो और थोड़ा दाल दो तीन
PNG pen, then graphene oxide also, and reduce the graphene oxide to treatment to the jute fabric. To characterize the untreated and treated fabrics, then to evaluate the physical and mechanical properties of the composite. And the materials, jute fiber with the plain jute fiber UD fabric, the plain woven fabric with an aerial density having 290 to 300 GSM and a thickness of 1.3 mm procured from ICR Kolkata. And polylactic acid in granules from used polylactic acid granules have been procured from Dekla Biopolymer Private Limited, Gujarat, India, and having density 1.25 gram per centimeter square. And then melting point also 160 to 170 degree and glass transition temperature 58 to 60 degree centigrade. Tensile also 45 megapixel and elimination at rate 2.5%. Effect strength 1.0 kilometers meter square. Then the advantages of polylactic acid: widely available and commercially produced natural thermoplastic polymer, and also cost-effective biodegradability and high mechanical strength, low toxic. Then we use graphene for the surface coating of the jute fabric. Graphene oxide and reduced graphene oxide have been procured from the takings to Yadnagar, Maharashtra. And some advantages of graphene oxide to enhance overall mechanical property, higher resistance, electrical conductivity, and UV resistance, and lightweight and processability also. And some the specification of the graphene oxide and reduced graphene oxides. Then this is the method of alkali treatment method to the jute fabric. Then first the raw jute fabric prepared, first clean, then storing. Then alkali solution, prepared solution using 5% and 10% solution concentration. Then immerse in the alkali bath at a room temperature like 1 hour and 2 hours. Then washing and rinse, remove excessive alkalis, and then drying air or oven dry. Then serial treatment like this: first clean the jute fabric, then wash into the remove surface impurities, then prepare a sealing coupling agent using using the methanol, and prepared a sealant coupling like APTS 3 aminopropyl triethylene sealant and two concentration. Then this sealant agent with methanol and distilled water using a metallic stearine. Then immerse the fabric for 2 hours in the sealant solution. Then remove the fabric from the solution and squeeze out excess liquid without using. Then air dried the fabric room temperature for a few hours. The next step is the graphene oxide and reduced graphene oxide treatment to the jute fabric. First clean the jute fabric, then dispersion of graphene oxide and reduced graphene oxide with distilled water to form a uniform solution. Then to use a magnetic stirrer to mix fuel and sonicate for a 1 to 2 hours to properly dispersion of the graphene oxide in distilled water. Then observe using a optical microscope and collect images also. Then step 2, immerse the jute fabric into the prepared solution of graphene and reduced graphene solution. Then maintain time up to 30 to 60 minutes to ensure uniform coating. Then remove the fabric from the solution. Then dry the fabric, coated fabric. Then further stabilize the graphene oxide for the settled. This is the images of dispersion of reduced graphene oxide. This is the probe. Use the probe sonicator 1 hour and 0.25% RGO. This is the probe sonicator 1 hour with 0.25% RGO plus sodium dirty cell. Without sodium, this is the image of without using sodium dirty cell. Because after dispersion, after 1 to 2 hours, then start to settle. So we use sodium dirty cell to reduce the surface tension, and the second image is properly dispersion with the distilled water. Then preparation of composite manufacturing process also. We use the PLA granules and the plain open jute fabric. This is the method of the composite manufacturing process. Then first dry the PLA granules at 50 degrees centigrade for 4 to 6 hours to remove the moisture. Then apply the pressure 850 psi or 60 kg per centimeter square and use temperature 170 degrees centigrade. Then dual or holding time 20 minutes and depends on the composite thickness. The part of the result and discussion is the water wicking test of the treated and untreated jute fabric. This is the UT means the untreated fabric means alkali treated, A means alkali treated, then S sealant treated, then AS alkali sealant treated, then AG alkali geo treated, then AR alkali reduced graphene treated, and then ASG alkali sealant graphene alkali sealant graphene oxide treated, then ASR alkali sealant reduced graphene oxide treated. In the vertic, this is the water wicking test of treated jute fabric, and the vertical fluid distance in mm and time is in mm. And we observe the alkali treatment is the highest, observe the water observance is the highest and UT is low, and very low in ASG and ASR sample. Then this is the tensile strength and tensile modulus test of composite. In this test, we observe the ASG and ASR sample. ASR sample provide the highest strength, observing the tensile strength method. And to composite due to the excellent interfacial bonding, uniform stress distribution and improved stress and along the load bearing capacity also. Then UT showed the lowest tensile strength and modulus due to weak interfacial bonding and reduced stiffness. And the result confirmed that the combined surface modification alkali cross sealant and the Geo and RGO significantly improved the tensile properties of the jute PLA composite. The next is the flexural strength of the flexural and flexural modulus of the rest of the composite. And flexural strength among all samples, the ASG sample and ASR composite show the highest flexural strength and flexural modulus. Geo improved the interfacial compatibility through hydrogen bonding and mechanical reinforcement also. And RGO improved the stiffness due to their higher graphic structure. And the nanofibers acts as a effective stress transfer bridge between the fiber and the matrix while reducing the interfacial slippage. And we see the same trend on the increased tensile strength in ASG and ASR samples. There is 4D harness test of the composite, jute PLA composite. At the highest harness was observed in the also ASG and ASR sample composite due to their synthetic effect of synergetic effect of multi-step surface modification, and the alkali treatment increased the surface area also, and sealant established strong interfacial bonding. The Geo and RGO derived reinforced the matrix at the nanoscale. So surface modification and graphene based nano reinforcements of sustainability enhance the shore harness and jute fiber, shore harness of the jute fiber PLA composite. This is the same images of alkali treated, ET alkali treated and Geo coated and RGO coated. This is the in Geo in untreated fabric. This is the surface is more smooth and alkali. This is the alkali treatment cell must show the increase in the rough area. The alkali treatment sample show the increased surface roughness due to the removal of hemicellulose lignin wax and other amorphous constituents. The Geo-treated sample displayed a thin weak and sheet-like coating deposited on the fiber surface, further increasing roughness compared to the alkali treatment. And the RGO-treated fibers exhibit a more compact and slightly aggregated morphology than the Geo and RGO samples. In the conclusion part, the combined effect of the alkali and sealant treatment along with graphene oxide and reduced graphene oxide incubation significantly improve the tensile property of the jute PLA composite, making the more suitable for the structural and load bearing applications. Among all the samples, the ASG sample and ASR showed the highest flexural strength and flexural modulus over the nanofiber and acts as a efficient stress transfer between the fiber and the matrix, minimize the slippage and significantly improve the flexural property of the jute PLA composite. And the last, the ASG and ASR composite again with the highest showed the harness the combined surface modification with nanoparticles incorporation enhance the showed the harness the effect of the hybrid treatment strategy improving the surface resistance and structural integrity. Thank you. If you use mass production like that, comparatively not more high. Not more high because we used 0.25 gram, 0.5 grams.
Thank you. Some
हाँ जी सर।
Good evening, everyone. My name is Sanjeev Menon. I'm a professor of practice at TIT, Panipat Institute of Engineering and Technology. So I have the privilege of presenting this paper. This paper explores whether infrastructural reliability may be influenced much earlier than traditionally assumed, that is traditionally assumed, specifically at the spinning and filament formation stage. So we propose that spinning, particularly for structured textiles and geosynthetics, may be viewed as a form of structural pre-engineering when integrated with predictive decision intelligence. So our framework links polymer biology, microstructural variability, creep mechanics, reliability calibration, and AI-enabled governance. So central to our hypothesis is that geosynthetics and structural textiles are widely used in reinforcing soil systems, embankments, slopes, and pavement reinforcements. Most research emphasizes macro structure, fabric architecture, and composite layering. So the stress has always been that perhaps the most important point that, the performance of geosynthetics in the field ideally should be studied at the fabric or the material structure architectural stage. What we are going to be talking about here is about the rheology. How is that influencing the performance of these textiles? So basically, what we are talking about here is that predictive control, and we'll be actually then involving ourselves once we've formulated this, once we've stressed the importance of rheology, we will be talking and suggesting a predictive control of rheology factors at the stage of filament manufacturing, because we feel that this is fundamental to improving and ensuring quality of these geosynthetics in the later stage. Now, the structural strength originates before the loom. That is actually what we are talking about here, that before the fabric is actually made, the filament at the stage of manufacturing, what its parameters are at that time, the rheological parameters at that time, that is going to define the strength and therefore the performance eventually at the, it is not as if this is the only thing that is going to define that, but this is sometimes ignored. So our focus, we are going to draw focus here, and then we are going to talk about the predictive analysis, the software part. So macrostructure, reinforced soil embankment, that is actually the end goal. The component is the geosynthetic grid and fabric architecture. Subcomponent is the extruded synthetic filament yarn. The microstructure is obviously the molecular orientation polymer melt dynamics. So currently engineering heavily emphasizes composite layering and fabric architecture. However, massive infrastructure failures or successes are rooted in molecular transitions. This is what we believe. So variability, whether from fiber lot heterogeneity or polymer rheological fluctuations, must be governed before the material solidifies into the load-bearing geometry. Now the physics of filament formation. So the polymer rheology dictates how molten materials like PVP, PP behave during extrusion, drawing, cooling. The key governed parameters include viscosity, which is the resistance to the flow. This influences the diameter. So diameter variability can occur at the filament stage. That is what we are stipulating. Shear rate sensitivity, how they react, the various layers with one another. This is going to the processing speed. This is likely to affect the molecular orientation. Then relaxation time, this parameter is also going to define the stress dissipation, internal stress dissipation, and then weak spots are likely to be created, and which may then when converted into fabric, these might get sort of exploited and resulting in low performance. Elastic recovery, material spring back determines crystallinity and draw ratio. Now we are going to draw an analogy between staple spinning and filament spinning. So in staple spinning we have fiber variability, and in filament spinning we have polymer batch variability. Drafting and sensitivity at the drawing zone in staple spinning may be analogous to draw ratio, sensitivity during the melt extrusion. Twist torque balance may be analogous to the molecular orientation balance that occurs during manufacturing of filaments. Unevenness dispersion is similar to, or we are going to take this as analogous to filament tenacity dispersion in the filament systems. So mixing governance, which is the fiber mixing, that is going to why I am drawing these analogs is because we have already a software that we've developed, which is based on cotton spinning systems, spun yarns. We have already made a successful software, AI enabled, which is being marketed by us, and now we are exploring at how this can be extrapolated into the filament systems. So mixing governance or fiber mixing is analogous to the polymer batch variations that may take place, resulting in differences and variability in performance of the. So tracing molecular stability to infrastructure safety, we are saying that polymer rheology stability, if you are able to maintain that, if you are able to maintain and turn that, have a tight control over that, then molecular orientation and crystallinity uniformity is likely to occur, which is going to result in controlled relaxation time, distribution, reduced dispersion in creep compliance, stabilized characteristic, creep modulus, rational durability and partial safety, calibration, enhanced infrastructural reliability. So controlling physics through predictive governance, data integration, this is how we've done already in the spinning, the cotton spinning systems. We have, what we do is first integrate data. We have, these systems that we have developed are not sort of standalone systems. They are integrated, very well used with already the existing, say the ERP, they can be integrated with those. The ERP, whatever information that the mail has, that talks about what mixings were used from time to time, what results were created. So these ERPs, the inventory, the production monitoring systems that are there, all of these are going to be, all these systems are going to be integrated with our model that we are proposing, that I'm going to be talking about shortly. So predictive modeling is about simulating fiber machine and polymer melt interactions to map tensile variability bands and viscoelastic creep response. So we are going to be monitoring those, and then from there we are going to be optimizing that. The information that we are going to be drawing from there are going to be used in So we are going to map molecular orientation, draw ratio, energy sensitive parameters, and from there then create a AI learning loop, and continuously we will be looking at the root cause of the variations and then attempting to reduce those in a continuous cycle as we go along. So moving from reactive memory to structured machine memory, that is what we are talking about here. So this is not reactive, this is not as if the fault has already occurred or and then we are looking at remedial measures. This is about actually mapping deviations as we go along in the system itself. Data intelligence will be governing, structural root causes will be found, retaining evidence to constantly recalibrate models and keep learning. So machines will be executing. So this is what we intend to reach. So again, I'll go back to the analogy between conventional spinning just to make this simpler and a little bit more understandable. So engineering logic was outcome-based testing. Here we are talking about AI-enabled predictive governance. Engineering logic, pre-production predictive modeling. So something which is not a post facto occurring incident, but it will be a continuous learning as we go along, so that whatever we are producing is better in quality. So performance validation is normally in conventional spinning verified after production. Of course, this is there in in filament spinning also. And but here we will be simulating before production begins. Material usage, over-design compensates for uncertainty. This often happens that if we feel that okay, a certain product is there in the field to be used, it may not be, there may still be an uncertainty factor as to how it's really going to perform, and then just haphazardly or without really having some proper framework in mind, it may be decided that okay, let us use it to say 85% efficiency to allow for the uncertainty that figures therein. So material usage is also going to be precision driven here. Excess usage is likely to be stored, is likely to be reduced. System learning was limited to in initial conventional systems, limited historical review. Here, closed loop AI learning will be there, continuous recalibration will be there. So the system itself will be continuously learning and evolving, and better it is expected to perform as more and more data gets generated. It will perform that much better. Risk management earlier was reactive correction. Now it will be predictive structural assurance. Now the spread of failure is likely to be reduced. I'm just going to show how. So reduced, the variability is going to be reduced. So the standard deviation improves the load sharing behavior and reduces stress concentration at structural intersections. This will help improve the creep predictability, stabilizing drafting, dynamics, narrowing the distribution of creep. Compliance outcome will be a narrower creep, rupture envelope, and vastly improved confidence in long-term strain predictions. The benefits of this. So rationalizing how this is done is, this is a theoretical example. Suppose we have existing coefficient of variation of say 8%, standard deviation of 8 kilonewtons per meter. Then we, if we govern it, say this reduces to 4%. Coefficient of variation, it reduces to say half. That is actually what we hope to achieve. And I mean, not exactly the percentage. This is an example which says that we will be, as we govern all of these parameters, there will be a reduction in these variations, and then the partial safety factor, it is likely to reduce maybe by 5%, 6%. The calculation is here. So this is obviously hypothetical, but this showcases as to how reductions improvements in performance are likely to occur, and they are rooted in improving the filament parameters. So what gains can we expect from this engineering sustainability? We can expect that material efficiency will be there. So polymer utilization may be less. Hello. Hello. Sir, textiles. So lifestyle sustainability validation. Now all of these are actually at the currently this is at an explorative stage, as I indicated earlier. But this has already been, the software that we developed for cotton spinning systems, for spun systems, is already being validated. This is very much into production. It's available. So wherein I will just talk a little bit about what those. I'll briefly touch upon that. So this is dispersion modeling, deepening the mathematical link between molecular standard deviations and safety factor recalibrations. This is by studying these, we will be reducing the variability on a continual basis, and the performance will be better. So software is being developed towards this. Every fiber whispers hidden variability that shapes yarn quality when it touches the machine and interacts with it. May I have the second? Decoding the science behind yarn quality in spun systems. So we have already devised this particular software that I am talking about, and wherein we predict profitability through fiber data excellence. Mixing is optimized. U percentage, unevenness percentage is also predicted at the very incipient stage itself, and then the cutting, the mixing costs are reduced, and the quality of the yarn is better, and also there is an improved ROI. So this is so there is more precision in mixing, and also the system that we developed. This is a dynamic system. There are real-time alerts that are passed on. Anytime deviations are seen by the system, alerts on desktops, on mobiles are passed on, and then the various parameters may be controlled then. So to wrap it up, I will go back to this, that perhaps there is always been more focus on studying performance, or basing our performance parameters on study of the final fabrics, or whereas the root cause may lay elsewhere. It may lay to whatever extent in the actual manufacturing of the filaments and the rheological parameters that are there. So it's imperative that we try and control these parameters, and the model that we are suggesting would be working upon this. It is under process to evolve a system that can govern, predict and govern these at the actual stage of manufacturing itself, so that various losses may be reduced and performance may be